implement measures to avoid accidents and their spread. To detect wideband oscillations, we have designed a wideband monitoring system based on power system phasor measurement methods. The system comprises master stations and substations, enabling monitoring, early warning, and protection against wideband oscillations over a wide area. We can see wideband measurement units distributed at the intersections of different power stations. These substations are used for real-time monitoring of the voltage and current waveform signals on the secondary side of the power grid. They perform basic data processing to obtain power grid data from different locations. Processed data is then collected and sent to the master station for analysis. The master station processes the data received from substations to perform monitoring, early warning, stability assessment, source tracing analysis, and others to obtain the overall operational status of the power grid. Here is the measurement method of the substations. The substation assess the secondary side of the power grid and obtain three-phase current and voltage waveform data. After analog to digital conversion and filtering, the data is transmitted to the data processing unit. The data undergoes adaptive frequency detection, then served as the frequency reference for mode filtering and phase measurement correction within the data processing unit. Finally, the data is processed and sent to the master station after integration. Compared to traditional PMU monitoring methods, this approach offers adaptive detection of synchronous oscillation components. It can detect vector of multiple frequency components. Considering subharmonics, it can accurately detect sub or super synchronous components. And the data transmission rate between the substations and the master stations is high, ensuring that the master station can accurately analyze the actual synchronous oscillation. The master station is responsible for calculating, organizing and analyzing data from the substations. Its function includes oscillation source tracing, determining the source and sink of each mode by calculating the power and sub or a super synchronous impedance for each mode. A stability assessment identifies the damping of each oscillation mode, calculates the system's aggregated impedance based on the measured data, and assess the stability of synchronous oscillations. Oscillation alert. When instability is detected, determine whether there is a risk of oscillation according to the oscillation criteria and issue an alarm. Through these functions, the master station can provide data support for sub or super synchronous oscillation protection and control. And this power grid consists of wind farms, photovoltaic power plants, and a thermal generator with a high penetration of renewable energy. And TQ and ULH are renewable energy collection stations. On January 18th, the wideband oscillation monitoring and control device at TQ station detected a multi-frequency sub-synchronous oscillation. The wideband oscillation sources and propagation paths are shown here. TQ, XA, and ULH station are multiple monitoring lines, and the voltage and current data are recorded. Through frequency stem tree analyze, we can determine that sub-synchronous oscillation frequencies of 8, 17, 25 Hz, and so on are present. Through impedance analyze, we obtained the resistance and reactance components of the frequency domain impedance in the range of 0 to 2000 Hz. In the range of 200 to 2000 Hz, the impedance component is positive, and the impedance at high frequency resonance points is positive damping. We can observe multiple segments of weak negative resistance in the sub-super synchronous frequency band. And the TQ station exhibits a weak negative damping in the sub-super synchronous frequency band, making it susceptible to oscillation issues. Above is the presentation of our work. Here is a conclusion. Impedance model analysis reveals a weak damping frequency band within the sub or super synchronous frequency range, posing a risk of SSO. The SSO monitoring and protection device effectively reduces oscillation occurrences, enabling real-time monitoring and system operation adjustments. Beyond monitoring and protection, proactive measures such as adjusting control parameters and installing stability control devices should address wideband oscillation issues. And finally, during power grid planning and design, a comprehensive risk assessment of wideband oscillations is recommended, accompanied by necessary adjustments to enhance the system's resilience against